Picture a platform like Kuaishou or TikTok where short videos and live streams coexist. Short videos are the fire hose of activity, billions of swipes, likes, and watch time signals every day. Live streams, by contrast, are where the platform actually makes money through virtual gifts and follows. But the behavioral data is sparse, new streamers are constantly appearing, and many users have barely interacted with the live ecosystem at all. So the natural question becomes, can we take what we know about a user from their short video behavior and transfer that knowledge into the live streaming side to fix the cold start problem? That is the puzzle this paper tackles, and the authors propose using multimodal large language models to do the bridging. Now, cross-domain recommendation isn't new. Past approaches generally fall into three camps. Some build transfer modules that share user embeddings between domains. Others use graph neural networks or sequence models to capture how items in one domain co-occur with items in another. And a third group brings in multimodal content, the video frames, the audio transcripts, the titles, to enrich item representations. The trouble with these multimodal approaches is that they typically use pre-extracted static feature vectors. They can tell you that a cooking video and a cooking live stream both have food in them, but they can't reason about why a particular user who watched a knife skills tutorial might want to enter a live stream where a chef is selling cookware. That deeper semantic reasoning is exactly what multimodal LLMs are good at, but dropping a 35 billion parameter model into a system serving 400 million users daily is a non-starter for cost reasons. So the authors design a framework called RGCD-Rep, Reasoning-Guided Cross-Domain Representation Learning, that solves three problems at once: how to use a powerful MLM affordably, how to keep its reasoning grounded in actual user behavior rather than free-floating speculation, and how to avoid negative transfer when short video interests don't actually translate to live streaming interests. Think of it like having a brilliant but expensive consultant teach a junior employee everything they know, then sending the junior employee to do the actual day-to-day work. The consultant only shows up during training. Here's how it works step by step. First, they mine real behavioral logs to find pairs of short videos and live streams that the same users engaged with in the same time window, weighting these pairs by behavioral co-occurrence and interaction intensity. Things like watch duration, GIFs, follows, comments. This gives them a data set of pairs that are empirically transferable from a user behavior standpoint. Then a frozen 35 billion parameter teacher MLLM looks at each pair and produces structured reasoning along three semantic dimensions: vertical domain, key subject, and content topic. For each dimension, it generates a label, an evidence description, and a match or not match decision between the short video and the live stream. These three match decisions get aggregated into a semantic transferability score. In stage 1, they distill this teacher knowledge into a lightweight 2 billion parameter student MLLM, but with an important twist. Instead of training the student on pairs, they decompose the pair-level reasoning into item-level supervision. So the student learns to independently describe any short video or live stream along those three semantic dimensions. This is crucial for deployment because at serving time, you want to encode each item once and store its embedding, not run pairwise inference. The student uses what the authors call learnable chorus tokens, a set of 16 special tokens inserted into the prompt that act as a multifaceted representation interface, capturing semantics more richly than a single pooled vector would. Training uses standard next token prediction on the teacher's structured outputs. Stage 2 is where the real cross-domain magic happens. The distilled student MLM now serves as a shared encoder for both domains, mapping everything into one semantic space. But here's the clever part. Rather than trusting that this single representation captures everything, they split each item into two views using two separate learnable query vectors that attend over the chorus tokens. One view is the transferable representation, the part of an item that's genuinely shareable across domains. The other is the residual representation, the domain-specific stuff that shouldn't be forced to match. Think of it like separating out the universal flavor of an item from its domain-specific accent. They then train these views with two losses. A cross-domain contrastive loss using InfoNCE pulls together the transferable embeddings of behaviorally co-occurring pairs while pushing apart unrelated ones. And here's the safeguard against negative transfer: a transferable routing loss. They combine the behavioral co-occurrence score with the teacher's semantic transferability score to rank all pairs, label the top 20% as high-purity transferable pairs, and the bottom 20% as low purity, and train a routing decision that decides whether a given pair should be matched primarily in the transferable space or the residual space. High-purity pairs get pulled together via the transferable view. Low-purity pairs get absorbed into the residual view where they can't contaminate the shared space. This is the key insight that distinguishes this work. Behavioral co-occurrence alone is a noisy signal, so they use MLLM semantic reasoning as a second opinion to decide which pairs deserve to shape the transferable representations. The experimental results back this up. On the Kuaishou dataset with about 110,000 users and millions of interactions, RGCD-Rep improves hit rate at 10 by roughly 17% and NDCG at 10 by about 31% over the strongest baseline, uni-embedding. Ablations show that removing stage 2 causes the biggest drop, and freezing the MLM backbone during stage 2 also hurts substantially, which confirms that you actually need to fine-tune the multimodal encoder on cross-domain pairs rather than just extracting static features. Gains are most pronounced on tail items and cold start users, exactly where you'd hope a cross-domain transfer approach would shine. And in online A/B tests on Kuaishou and Kuaishou Lite follows improved by 0.83 to 0.93%, with steady gains in clicks and effective room entry rate, which are meaningful numbers at this scale. That said, there are real limitations worth flagging. The teacher MLM's reasoning quality is taken somewhat on faith. There's no rigorous evaluation of whether its 3 semantic dimensions actually capture the right notion of transferability, and the structured prompts are essentially handcrafted. The routing label construction uses fixed top and bottom percentiles, which is a coarse heuristic that throws away 60% of the training pairs as uncertain. The framework assumes a clean source target asymmetry from short videos to live streams. But real platforms have bidirectional and multi-domain transfer needs. And while the final embeddings are deployable offline, the training pipeline still requires a 35 billion parameter teacher model and substantial GPU resources, which raises the bar for who can replicate this. Looking forward, the most interesting open question is whether MLLM reasoning can be used not just for offline representation learning, but for more dynamic query time personalization without breaking latency budgets. Now let's walk through some questions you might have after hearing all of this. First, why decompose the pair-level reasoning back into item-level supervision in stage 1? Wouldn't it be more powerful to train the student on pairs directly? The reason is purely practical for deployment. If your student only knows how to reason about pairs, you'd have to run it on every possible short video live stream combination at serving time, which is computationally impossible. By training it to independently describe single items, you can pre-compute one embedding per item offline and store it. The pair-level transfer logic then gets handled in stage 2 through the contrastive and routing losses, which operate on those pre-computed representations. Second, what's actually new about the transferable versus residual split? Haven't disentanglement approaches been done before? You're right that disentangling shared from domain-specific factors is an old idea in cross-domain recommendation. What's distinctive here is the supervision signal for the disentanglement. Most prior work disentangles based purely on behavioral patterns or adversarial losses. This paper uses the MLM semantic transferability judgment as an independent second signal that combines with behavioral co-occurrence to decide which pairs are genuinely transferable. So the residual view doesn't just absorb statistical noise, it absorbs pairs where the MLLM's reasoning says the semantic match is weak, even if the users happen to engage with both. Third, why use chorus tokens instead of just taking the final hidden state or pooling? A single pooled vector forces all the semantic information about an item into one direction in embedding space, which becomes a bottleneck when you want to extract multiple views, like transferable versus residual, from the same encoding. The 16 chorus tokens give you a richer multi-token interface that the downstream query-aware aggregation can attend over selectively. Different queries can focus on different chorus tokens, which is exactly what enables the clean separation between transferable and residual representations without needing 2 separate encoder passes. For large-scale recommendation systems serving hundreds of millions of users, The most directly applicable lesson here is the offline distill then serve pattern for incorporating LLM reasoning. You can't put a 35 billion parameter model in your serving path, but you can use it during training to generate structured supervision, distill into a small encoder, and pre-compute embeddings that get indexed for nearest neighbor retrieval. This same recipe applies to candidate retrieval across any domain boundary, from search to recommendation, from videos to products, from articles to ads. Wherever you have a source domain with abundant signals and a target domain that's sparse or cold. The transferable residual split is particularly useful in production because it gives you an explicit knob for handling negative transfer, which is the silent killer in most cross-domain launches. The other practical takeaway is the use of LLM reasoning as a second opinion to filter noisy behavioral signals. Production recommendation teams constantly deal with co-occurrence data that looks meaningful but actually reflects exposure bias or session-level confounds. Using a multimodal LM to independently judge whether two items are semantically related, and then combining that with behavioral statistics to construct high-confidence training labels is a pattern that could improve everything from related item models to query document matching to user cohort definitions. It turns the LLM from an expensive inference component into a cheap one-time data refinement tool, which is exactly how recommendation teams should be thinking about leveraging large models today.